collisions in one dimension. So let's go over elastic versus inelastic collisions. A but before we do so, we have to go over the conservation of linear momenta, which is pretty much what we cover here. So when two objects collide, momentum can transfer between them. If the system is isolated, no external net forces, total momentum is conserved, and we'll get into that a little bit later. But the sum of linear moments is the same before and after. So I guess we learned that in 7.2, but I guess the derivation of it would be that, remember, impulse, which is force, applied over time, is equal to mvf minus vo divided by t. I just in my head. So wait. Sorry, no, it's just a change in linear momenta because we multiply time on both sides, so it's mvf minus vo. And if there is no linear momenta, where the impulse is zero, then mvf is equal to mvo, because these two terms have to be the same in order for this to be zero, according to the zero product property rule. And again, you can expand this however much you want, because let's say that we have linear momenta 1 or impulse 1, let's just say, so f1t plus f2t plus f3t plus f4t and so on and so forth. It's just the sum of linear momentas, so it's just going to be I guess v1f minus vof, and just the sum of linear momentas over and over. But if this is all equal to 0, then all these terms must be 0, meaning that the initial position is equal to the final position. In other words, the sum of linear momenta will always be conserved before and after the collision, such that mvo is equal to mvf. And we get into this a little bit more because we usually get a varying mass and varying velocity, but the product between these two will always be equal to the product between these two, and that's the beauty of math. And yeah, I think that's pretty interesting. Elastic collisions mean that kinetic energy is conserved. In all three cases, momentum is always conserved because we assume that no impulse is applied. Remember, impulse is just force times time. Inelastic means that kinetic energy is not conserved. Completely inelastic means that the greatest kinetic energy is lost and the two particles stick together. So when macroscopic objects, cars, blocks, people collide, some energy becomes heat due to internal friction, which is why we do lose kinetic energy, because work is done. And remember, work, if we do work, that's related to the kinetic energy. And if we're doing work on the surrounding, it's technically a negative work relative to the system, which means that you just times negative on both sides. And basically, in other words, we are losing kinetic energy if we do work. So formula right here with two bodies, of course. And I say I for initial and F for final. So in other words, again, if two things are moving at certain speeds and have certain momentum, those two bodies, the sum of the linear momentum of the two bodies after and before must be the same. And again, that was proven using some algebra before. This one is just some simple logic. It's just relative velocity. I mean, yeah. For I guess you can do some algebra, but in other words, the difference between the velocities of two bodies will always be the negative change in velocities of the two bodies in the final position, or after the collision. You would say the lighter object tends to rebound more dramatically because, again, it's pretty logical here when we use conservation of linear momenta. Like, let's say that well, I guess we can just use a lighter body in general without having to do a two-body collision. Let's say the body's mass is 0.1, and let's say it's perfectly inelastic. All right, let's just say that it drops. Wait, how would I? Okay, yeah. Well, yeah, okay. Let's just say it's completely inelastic. So let's say it's 0.1 with it's moving at 50 miles per hour. Or sorry, 50 meters per second, because that would be the SI system for velocity. So let's just assume that this is a 0.1 kilogram body moving at 50 meters per second, and it collides with a, let's just do something simple, so 49.9 kg body here, and it's completely inelastic, meaning that all the linear momentum is transferred here, which it always is. So this will have to be equal to the sum of the bodies, because when collisions are completely inelastic, that means the bodies combine together, as mentioned before. So it's going to be 0.1 plus 49.9. And there's a reason I chose 49.9, because that sums up to 50 is equal to x. And if we use some logic, we could solve for x, or I guess it would be VF in this case, because it's moving as one body. And here we're doing it as one body, but we'll learn in the other video that you can change it to another body. So this is just 50, and so 50 times 0.1 divided by 50 is equal to 0.1, meaning now that this object is moving at 0.1 meters per second. Quite interesting. We see here that a small body with very high velocity barely moves the thing. And you see that in real life. Like, imagine me hitting a tank with a ball or something. It will barely move. I don't think it'll move at all, actually, because of friction. But yeah, completely inelastic collision, we just did that example there. So yeah, that's all for 7.3.